Okay, welcome back. Happy Friday. I'm glad you guys are all here safe and sound. We got a few folks who emailed me and said they just couldn't get here safely, and I appreciate that. But you guys are here, so we're going to do what we had planned to do, which is differential equations. Just a couple of announcements first. The the take-home quiz is due, so go ahead and throw it right in the folder right now for me. Also, project number 2 is officially assigned. Make sure you grab one from your tables. They should all be out there already. Project 2 is going to be collected on February 12th, which is 1 week from today. Right? So that project is due 1 week from today. And as with all the projects, you are welcome to and encouraged to work with other folks, including each other and people in the studio, etc. Just one other heads up. Quiz number 2 is due on Wednesday, February the 10th. Now, normally I will hand you the quiz, the class before it is due, except for this one, which I actually handed you on the first day of the semester. It is the first page of this particular packet. So you can take a quick look at it now if you want to, but you already have quiz number 2. It is page 1 of this packet. It is unusual in that it is the only quiz that you can take multiple times. It is the only quiz that I gave you the answers to, and it's the only quiz that you are grading yourself. The rules are all clearly written in the first paragraph on page 1 of this packet, but it is essentially just a show me that you have memorized the common derivative and antiderivative formulas, okay? If you need more copies than I have provided, go on Moodle and just print the quiz. Okay, right. So the quiz is due Wednesday. The project we just handed out is due Friday. All right, so today is our introduction to differential equations, and I think that is all we need to say about that. So we're starting here at the top of page 45. In this class, we solve differential equations and initial value problems, including problems related to motion. So there will be some connections between the stuff we do today and the stuff you did in your physics class about projectile motion, which was probably very early in physics last semester if you took 111 here. All right, number 1, a differential equation is an equation involving derivatives. That's the definition. For example, a satellite has a constant velocity of 80 meters per second. We can translate that fact. If we let s of t represent the position of the satellite at time t, meaning its height or altitude, how far from the ground, then we can write the derivative of position with respect to time is equal to 80. And we know that the derivative of position with respect to time is velocity. And so this right here is a very simple differential equation because it's an equation involving a derivative or multiple derivatives. And the solution to this differential equation is also fairly easy. The solution is just the function that satisfies this differential equation. I want someone whose derivative is 80. 80x is good, but there's no x in this one. T. 80t. There's the solution. We have just solved our first differential equation. All right? Any other solutions to this one? Yeah, +7 or plus c in general. So differential equations typically have many, many solutions. But that is what we're looking for. It's just a function that satisfies that equation. When you take the derivative, indeed, you get the 80 that we were hoping to get. Number 2, they can get much more complex. For example, y double prime minus y prime minus 12y equals 0. In your head, you are imagining something like y equals x to the 5th. Like that is not the solution, but I'm just making something up so that we're clear what it means to have a solution. If this indeed were the solution, then if I take the derivatives, so 5x to the 4th, and then 20x cubed, yeah, and I plug all of that stuff into the differential equation, I should get something which is true. All the time is true. It is identically true. And so in this case, y double prime is 20x cubed minus y prime, let's see, that's 5x to the 4, minus 12y, that's x to the 5th, equals 0. Looks like an equation I'm asking you to solve. That is not what we're after. Oh, x to the 5th times 12. Thank you. 12 times y. 12 times x to the 5th. Okay, equals 0. We are not trying to solve that equation. This equation is either true for all x, or we did not find a solution to our differential equation. And that equation is not true for all x. It's true for some x's, But that's not what it means. It means the equation, this y double prime equation, is supposed to be true all the time, and it wasn't, which means x to the fifth was not the winner, right? So in English, this is saying, find me a function so that when you take its second derivative and subtract its first derivative and subtract 12 times the original function, you get 0 all the time. It's a lot more complicated than the STT equals 80. Okay, let's see. So what kind of a function might work? Well, definitely not a polynomial, because that x to the fifth is never going to have a chance to cancel with anyone, because when we first take its derivative, the power goes down, right? And we need all of these x's to magically disappear, and they aren't going to for any polynomial. Other possibilities, like derivatives who don't really change too much because we need all this stuff to cancel and get 0. Any thoughts on? Yeah, Chris? Isn't that a really nice candidate? Because maybe somehow the second derivative minus the first derivative and minus 12 times the original will all magically cancel because they're kind of comparable to each other, whereas x to the fifth is not going to cancel with this x to the fourth term. So e to the x sounds good. We know that all the derivatives of e to the x are just e to the x. So let's just see if e to the x is maybe going to work. So second derivative is e to the x. First derivative is also e to the x minus 12 times the original function, e to the x. Is it always equal to 0? No, but at least we had terms that were canceling each other, right? There's cancellation that happens here. So I will provide you one solution. It looks an awful lot like e to the x. The one that I will provide is e to the negative 3x. Let's try this. So I'm pulling that out of a hat. I hope I'm correctly pulling it out of the hat, but we're going to find out. And we're going to take a couple of derivatives. What's the first derivative? Negative 3 e to the negative 3x. Second derivative, 9 e to the negative 3x. And then we're going to plug all of that into the original and just see if the original equation is true. So y double prime becomes 9e to the negative 3x. And then it says minus y prime, so minus what? Negative 3e to the negative 3x, so that's going to become a plus. Minus 12y, minus 12e to the negative 3x equals 0 with fingers crossed. Does it? It does. Yeah, it's identically equal to 0. So indeed, e to the negative 3x is a solution to that differential equation. So how did I come up with it? Well, I'm just so smart. Or possibly there's an easy procedure that I did in my head in a half a second. So there's an entire course on this kind of stuff. It's called differential equations. I've taken it. Perhaps you guys will take it one year from now, next spring. But in the meantime, you don't need to worry about pulling them out of the hat. But if I happen to hand you something, it should be easy for you to either verify it is a solution or tell me it is not a solution by doing just what we did here. Okay? So the goal for today is not to say, can you come up with e to the negative 3x? But if I give you e to the negative 3x, you should be able to tell me whether or not it worked. All right, so the differential equations that we are going to solve are going to be simpler than that y double prime one. Our differential equations will have the form dy dx equals some stuff involving x's. And then the goal is to find a formula of the form y equals some other stuff in terms of x. So for example, number 4 is more along the lines of the differential equations I will ask you to solve. Let's see if we can find a solution to the differential equation dy dx equals cosine of x minus 1. So we're looking for some function whose derivative is cosine of x minus 1. Well, let's see, what's the opposite of taking the derivative is taking an antiderivative. So how about we think about taking an antiderivative of both sides of this? Antiderivative of cosine, being very careful. Sine, being very careful. It's quite easy to make a mistake with the signs of our antiderivatives of sine and cosine. Antiderivative of minus 1, negative x. What's a good name? I appreciate that. What's a good name for this thing? Y is a wonderful name for that thing. And if you take the derivative of that thing, then magically you'll end up saying, oh, dy dx equals cosine of x minus 1, which is exactly what we wanted. Damn. I would love a plus c. So it says here, how are the different solutions related? Well, it's the same thing we talked about the other day with all this vertical shifting, right? So there's infinitely many solutions to that differential equation. They all look like that for some choice of this number plus c, okay? Super. Technically, the question that I asked, you could have omitted the plus c. I said, what's a solution? Well, we had one there without the plus c. There were many correct answers to that problem. Okay. To get a specific solution, we need some extra condition. It's called an initial condition or an initial value. It's written in symbols here. They'll make more sense with specific numbers. So we're going to solve the same differential equation we did a moment ago. And y of pi is supposed to equal 1. Okay, let's write down the general solution we just had before. What was it? Y equals sine of x minus x plus c. That's what we had just written. And what I want us to do is pick the right value of c to make this true. Y of pi equals 1. Now, y of pi might look quite funny. This is the more standard way to write it, f of pi, but we're now just going to kind of use the letter y a little bit and treat it just like our function notation f type thing. So what does that mean? Pi is going in for what letter? X, and 1 is going in for what letter? For y, and we will be left with an equation we can solve for c. So here we go. 1 is the y value equals sine of pi minus pi plus c to be determined. 1 equals sine of pi is 0 minus pi plus c. Add the pi to both sides. And it turns out that c is 1 plus pi. The solution to the differential equation has to look like blue. So don't stop just because you have c. You got to write the answer to the differential equation. So y equals sine of x minus x plus the c that we just found over there, 1 plus pi. So that's our solution. If you take its derivative, you'll get exactly what we wanted, the cosine x minus 1. And that particular function does pass through the magical point, which was pi comma 1. Lots of vertical shifts of the same function. Okay. The problem, the differential equation plus the extra condition altogether is called an initial value problem. Those two pieces together make what we call an initial value problem. All right, so we were promised some physics at the start of this class, so here we go. We know that velocity is the derivative of what? Position. Also, blank is the derivative of blank. Acceleration is the derivative of velocity. Okay, so we're going to use those facts. Here's the problem. Suppose a ball is thrown upwards from the edge of a cliff that is 100 meters above the ground. Translating that into an equation, s of 0 is 100. S is going to be our standard letter for position. So its initial height or position is 100 meters off the ground with an initial velocity of 74 meters per second. So v of 0 is 74, right? 0 is the initial part. Taking gravity is negative 10, 9.8, close enough. Negative 10 meters per second squared, which we can write as a of t is negative 10 for all t. We're going to derive the formulas for the object's velocity and position, and then we're going to answer some question over here. Now, many of you already have physics formulas memorized. You might have seen them on the first day of Physics 1 last semester. So now we're going to close that gap. Whatever disbelief you had when Ted shared those formulas with you in the beginning, we're gonna solidify it now and make sure that we buy all of these magic formulas, but we're not going to use them here. We're going to prove them from first principles. Okay, we're going to start with this guy right here. A is equal to negative 10. But we're going to say, okay, we're going to change this a because we know that acceleration is the derivative of velocity. So instead of a, how about dv dt equals negative 10? Buy it? Okay, and we're going to say, hey, that's a differential equation. And we know tons of stuff about differential equations now, so we're going to find the general solution to this differential equation. Give me a function whose derivative is negative 10. Negative 10x, but not x here, t. It's always the variable in the bottom of the derivative notation. We want to be very general here, so what are we sticking at the end? Plus c. And what is a good name for what we just calculated? D, right? That's our solution, our general solution. Okay, before we go any farther, I want to get my hands on the actual value of c. I want it to be specific. So we're going to use the initial condition that's given right here. V of 0 is 74. It's the same idea as the y of pi equals 1 that we used up above. So then we'll come down here and we'll say, okay, instead of v, what number? 74 equals negative 10 times, instead of t, what number? 0. And then plus the c, which we're about to find. How much is the c? 74. Super. So then copying this formula again, in fact, we'll copy it up above. Copying this formula now, we get v equals negative 10t plus 74. That's our velocity formula. Okay, let's change this v into a derivative of some flavor. What is v the derivative of? S, right? Velocity is the derivative of position. I'm just going to copy the right-hand side. Okay, hey, it's a differential equation. We're going to find its solution. Antiderivative of negative 10t. This is not quite as easy as the one that we did before, but this is our power rule. What do we do with the power? Add 1, so it becomes 2. Divide by new power, which is 2. What about that negative 10? Stays there. Constant multiples get copied. And we'll clean that up in just a second. Plus someone whose derivative is 74. 74t plus, very general, c. It's not the same c. I said we were going to make lots of uses of the same c, even though it's not. So this is not the 74c that we found before. It's a brand new c, but we'll just call it c. What's a good name for this guy? S. That is the position. That is the solution to the differential equation. Okay, so next up is to find this particular c. We had one other piece of info. What did it say up here? S of 0 is 100. Initial height was 100. So we're going to plug that stuff in. So here we go. S equals, all right, I'm going to change that negative 10 over 2 to a negative 5. T squared. T, I should have changed my S too. S becomes 100. All the T's become 0. So negative 5 times 0 squared plus 74 times 0 plus the C, which we're going to find. C is 100. Lovely. And then we'll just copy this guy. S equals, again, changing the negative 10 over 2 to a negative 5, t squared, plus 74t plus 100. Now, I had said that you guys saw physics formulas in the very beginning of physics 1, and I'm guessing that one of them was this. S is equal to 1/2 AT squared plus V0t plus S0. Does that look familiar? Yeah, and so here it is. V0 times t, initial velocity times time. Where is that in ours? 74t, and the 74, it became the value of c because the t equals 0 blanked out whatever happened to be elsewhere in the equation. So yeah, the initial velocity is always going to end up there. I have a plus S0. What is that? 100. It's always going to be that guy because plugging in t equals 0 is going to blank out all the stuff before the plus c. What about this -5? Where'd that come from? It was half of the acceleration. And why was it half? Because we added 1 to the power, that gave us the t squared, and we divided by 2. And all throughout physics, you see these halves floating around. And in many of those cases, it is simply because you are doing this power rule. You have a something squared and a half in the front. I'm going to write part of a formula here, and it's part because I don't remember what it was. Is that anything? What is that? Kinetic energy? Is there a letter for KE? Okay. I don't know why this formula is true. I memorized it at some point when I was a physics student, but I can just about guarantee you that that v squared and this 1/2 came from taking 2 antiderivatives. Okay. All right, so there was a follow-up now that we've got all the calculus done. Let's see, it says we're going to figure out how fast the object is moving when it hits the ground. So we have all the pieces that we need. We're going to highlight the 2 formulas that are the finished formulas here. So we've got our position formula there, and then our velocity formula slightly off the screen up here. I'm going to copy that guy down below. B equals, what was it, -10t plus 74? Great. Okay, so these are the 2 formulas we'll need. And it says we want to know how fast the object is going when it hits the ground. So let's figure out the when it hits the ground part first. When it hits the ground, do you know something about the velocity or about the position? Position, it is 0. So that's the first step. So we change in the yellow equation, change the s to 0, copy everything else. How would you solve that equation? Quadratic formula, right? And maybe it factors, but probably it doesn't. So I suspect many of you have played around with Wolfram Alpha, but if you haven't, this will be our first chance to just look at it together. Just Google Wolfram Alpha, type in the equation 0 equals -5t squared, what was it? Plus 74t plus 100. You don't have to worry about syntax, you just kind of type it in the way that it looks. Great, there's the graph of the parabola. The zeros are these red dots here, right? This guy doesn't make sense in our problem because it's a negative, right, backwards before the experiment started. Here are the exact solutions. That's not so useful to us, so you just click approximate forms and it says, okay, those are the 2 numbers. So 16.046, just write that down. T equals 16.046. If you like more digits, you just click the more digits button and you'll get lots of digits. Right? Okay, what was it? 16.046. Thank you. Okay, so that's approximately. So that's the. Oh, you're right. All right. Okay, good. And then the question said, how fast is it going when it hits the ground? So that's the when it hits the ground. What do we do with it? Velocity. Plug it into velocity, and then we'll have our answer. So v is about -10 times this guy plus the 74. What do we get? Am I doing something wrong? Yeah, I messed up here. Let's try this again. Wait, 16.046. Yeah, that's okay. All right, one more time, Mario. -80.46. That's a velocity, so meters per second. Great. Negative because down. Right? Okay, so even though many of you had already memorized one of those red formulas up there, half AT squared, that business, I might still ask you to just from first principles do some antiderivatives like we did here, okay? So just make sure you're comfortable understanding that the starting point for this and all problems like this with projectiles is the constant acceleration. Start with the constant acceleration, 2 antiderivatives and a couple of plus c's later, you'll have your velocity and position formulas. Yeah, absolutely. I mean, if you are given the position function, this yellow guy, you could take two derivatives and you will get the velocity is this guy and the acceleration is -10. But you would have done that last semester in Calc 1, and now we're going the harder direction in Calc 2. Okay. All right, the activities start on the next page. Raise the flag if I can help.